So next I want to show you an example of a misleading chart. There's lots of different ways to represent data accurately. There's also ways to represent data that's misleading. And this is very common, especially in news publications, magazines, on the internet. Politicians do this all the time. And so you really want to be careful that you're not misled by a displaying of data that's just not quite right, okay? And so it's very easy to do. Sometimes it's done on purpose, and sometimes it's done accidentally. And so you just want to be aware as a viewer, as a consumer of data, that you're not being misled because of a strange, inaccurate representation. Or maybe it's accurate technically, but it's just misleading because it gives you the wrong impression of the data. So let me show you an example here. I've got the population of the state of Michigan over the last 80 years, and it's split up into different 20-year chunks, basically. So 1940, 5.3 million, 1960, 7.8 million, so forth, all the way down to 2020, there's about 10.0 million people, rounded to the nearest 100,000, essentially. And so one way to represent this would just be with a bar chart, bar graph, or like a frequency distribution sort of thing. More bugs flying around me. Weird. Anyway, so here's an example of how you could represent this data with a bar graph. Okay. Now this is actually not inaccurate. It's an accurate representation. I kind of sketched this out ahead of time. But there's something very misleading about it. What you'll notice is that the y-axis, the vertical axis, doesn't show all the values, right? It starts at 5 and goes to 10. And so the height of the bars is skewed a little bit. Well, actually quite a bit. The bar that represents 5.3 million is significantly smaller than the bar that represents 10.0 million. Now think about this. 5.3 million is over half of 10 million, right? But that's not what this bar represents, right? The height of this bar is significantly less than half the height of this bar, okay? Significantly. And so it gives the appearance of a much larger jump from 1940 to 2020 than actually occurred. It looks like proportionally that this multiplied by 5 or 6 to get to get that height, when in reality it was less than double, okay? And so it's just very easy to mislead people with a quick visual. This is accurate. There's nothing inaccurate about this. I do have a bar that goes up to 5.3 on the chart and 7 point, whatever it is, 8, and roughly. I mean, this isn't perfect because I didn't use a ruler and graph paper and stuff, but it's close. And so this isn't completely inaccurate, but what's really missing here, well, there's two things you could do. One thing is I could have put a break in the graph. And some people will do this. It doesn't really change the fact that it's misleading. I could have put a little zigzag on the axis there, and that sometimes will represent a break in the graph. Sometimes that is helpful, but other times, it's still easy to miss. And it still doesn't really give you a good visual picture of the relative sizes of those populations, okay? So what would you want to do instead? Well, generally speaking, you would want to fill in the rest of those bars, right? You'd have this go down, each of these bars would really come down to about here probably. And if that was the actual bottom line, this would look much more proportionally representative of the actual population of the state of Michigan, okay? So you want to be careful, and so be careful not to do things like that, which can be misleading, but also be careful not to be misled by others doing this, okay? So it goes both ways. Sometimes, though, you can't really avoid it. If I was looking at some other values where you really just can't fit all of that chart on a practical, a page of a magazine, for instance, or a website would just, you click on the website and the whole screen would be like all these bars that are just like completely overwhelming. There are times where it's reasonable to cut some of that data out or cut some of the size, the length of those things. But it should be noted in there or stated some way that's very clear. It says, the relative size is not accurate, in a way that's not intentionally misleading the viewers or the consumers of that information, okay? This is an example where you could do something misleading intentionally or accidentally, either way, to skew that data. There are many other ways that data can be technically accurate but misleading. One of those is to use, instead of a one-dimensional, like a bar like that, it's technically two-dimensional, but the width is all consistent. Another way is to change both the height and the width, or the height, width, and depth, and make it like a three-dimensional image. And that can be very misleading, because even if you had, let's say you had a bar that had a height, one was half the height of the other, for instance. Ugh. That's not bad, right? Those two are roughly half of each other's height, or half of each other, right? You can't do that. One is half the other's height. However, that one's a little wider. And so that kind of makes sense. If one's half the height, but they have a consistent width. But one thing that's also misleading is to take the width of the other one and change it as well. So you have double the height and double the width, right? So you could have something that looks like this versus something, actually, let's just change it here. If I were to double the width and make it double that width. All right, so here I've doubled the height and the width of that. But what does that really do to an area? What you're seeing visually is the area, so it's actually quadrupling. It's multiplying by 4, right? So the area of this first box, or first bar, is 1/4 the area of the bigger one. And so when you double and double, you're really multiplying the total area by 4. And so that can be misleading if the actual value is only doubled. Even worse if you add a third dimension to it. So if I had a box here, like a rectangular solid, on my chart, and a lot of these you'll have 3D charts, and so that can be really misleading if you had a 3D shape here, and then you doubled all of the dimensions. Right, so let's say that depth is also double. It's probably a little more than double, actually. I could probably cut that down a bit and still get the same effect. Well, if you double the height, double the width, and double the depth, you're really taking 8 times the volume. And what your perception, you perceive the volume more than just the height, okay? So these are different ways that people can mislead, can give misleading representations of the data. Okay, if a certain bar would be double the size, but you double all 3 dimensions, all of a sudden it's really 8 times the volume, and that's what you perceive, even if it's really just double the number. So those are the types of things that can be misleading, just the shape, but also things like the x-axis. If it's not a consistent gap between here, if I had 1940, 1960, 1980, and then 2000, 2010, or something like that, it's 20, 20, 20, 20, and then a 10-year gap. Things like that, those can be misleading. So different tweaks in the data, there are lots of different ways to mislead or give misleading representations of data that are maybe technically accurate, or maybe they're not accurate, maybe they're false to begin with. But just be aware of that, and practice. I'll give you some practice in the homework where you can try to identify some of that stuff.